I'm James Jackson, and also with me is Alfonso Escobar, and we both work here at IDIADA. Alfonso manages global projects in vehicle dynamics, and I am part of a dedicated team of human factors experts here at IDIADA. And today we're going to be looking at an experimental approach we're using with our simulation facilities on comfort for autonomous vehicles. So for those of you who don't know, IDIADA is an automotive industry partner, and we offer pretty complete solutions through research, development, and also testing, principally from our headquarters close to Barcelona, but we also have a presence worldwide with around 2,500 people working on various client and partner projects. And yeah, if you'd like any more information, then feel free to check out the virtual exhibition area, where we'll be happy to give you any more information. So yes, next slide. Sorry, Alfonso. So today, what we're going to be looking at is based around the development of connected and autonomous vehicles. So there's some key challenges here, and this is one of the key things that we look at, particularly from a human factors perspective, is the development that has been pushed by technology without the human possibly always being at the center of what's being developed. And that's of a key consideration when we start to look at how connected and autonomous vehicles will coexist within the transportation system, and how they'll interact with both passengers of those vehicles and also other road users. And a key question here is the acceptance of the technology, and there's a few key components to that. The acceptance of the vehicles themselves, the ethics of their use, also how we influence the emotions and the comfort of passengers. Sorry, next slide. And that leads us to the key question: how we can enhance the public acceptance for when these vehicles will enter into the marketplace and onto the road. And the way that we do that is through a human-driven design approach, where we keep the human at the center. Next slide, please. So the project that we're working on here is called Suave. It's a European project funded by VIC2020, which IDIADA is part of a consortium of another 9 partners. So the project is focused around a human-centered design approach, and we're working on development for future autonomous vehicles. Next slide. So this is split up into a series of key work streams. The first of these is social and physiological research on this general idea of cab acceptability. So that's looking at all those components of vehicle acceptability, the ethics of use, emotions, and comfort as well. And also a key part of the project is the development of a human-to-centered design platform, which will allow us to undertake research and also evaluation of different systems. 2 other key outputs of the project is the development of a cross-functional framework, which intends to set out a series of guidelines for the integration of ethics and legal issues when these kinds of vehicles are on the road. And finally is the development of a vehicle concept known as Alfred, which intends to humanize the interactions between potential users and these connected and autonomous vehicles in the future. So next slide. A key question of this project, looking 10 to 15 years in the future, is how to put the human in the center of the development without having a functioning cab or a representative environment of how roads might look like in the future and how people may behave on them. And the way we can do that is through simulation. I've already mentioned the virtual centered design platform that is being developed as part of the project, but a key component for us is the use of our own DIM250 simulator, which we're also using in parallel with aspects such as virtual reality for immersive displays of the vehicle interior, and we're using this for both research and evaluation throughout the project. So just to summarize further on the IDIADA role, there's 2 key components. The first of these is leading the development of the evaluation framework for the entire project. So this again is covering all of those key aspects of acceptance, so ethics, emotions, and comfort. And then also we are leading the development and investigation around comfort, which will then be integrated into the Alfred Concepts developed as part of the project. Next slide, please. So just to briefly touch on the Alfred concept, this is based around the passenger and is split into two different units. The first of these is an empathy unit using sensors and other kinds of technology to try and estimate passenger emotions and their cognitive state and then recognize what that is. And then secondly is an interface known as ACE, which is integrated within vehicle functionalities. And the idea here is to have an adaptive control strategy, which is then based upon cognitive and emotional states of passengers. And then this, for us, is split into two separate areas. The first of these is the ambient cabin environment of the vehicle, so looking at other aspects such as occupant posture, but then also dynamic motion comfort of the autonomous vehicle itself, which Alfonso is going to run through our methodologies and the work that we've been doing on this in some more detail for you. Thank you very much, and I'll hand over to Alfonso.
Thank you very much, James. Okay, so I will be explaining the details of the work that the vehicle dynamics and the human factor teams have been doing with regards to the evaluation of ride and comfort in our driving simulator. And in the following slides, I will be covering mainly the 5 topics that you can see on the screen now. So I will explain the motivation that we have in this project and the hypothesis that we are setting in these experiments. I will take you through the way that we set our experiments and regarding the scenarios and how we use our model predictive controller to run these simulations. We'll give you an overview about the methodologies that we use to collect the both objective and subjective data from the passengers or the participants in the experiments. And we'll also give you some explanation about how we are approaching the data analysis. We'll finish with some controls on some steps of the project that will be interesting. Okay, so let's go through our motivation. James already introduced the concept of Alfred, and here we start from the consideration that the trajectory that the autonomous vehicle is going to decide to follow and the way that it's going to execute that trajectory is going to have a direct influence in the passenger's ride comfort. So what we intend in this project is to make sure that when Alfred is designed, we include all these algorithms and criterion to be able to take into consideration the expectations of the passengers for ride and comfort, and to also to operate and modify the way that the controller is working to reach actually that level of comfort that we were intending to have. So our solution here, the other proposal for this project is to use an Mpc Motion Controller that we have been working on in the last couple of years. Our controller is actually divided in 2 Mpc controllers. One that we call the trajectory optimizer that actually looks at predefined trajectory and kind of optimizing and smoothing the levels of accelerations and many other variables to make it better for the passenger's comfort point of view. And then we have another Mpc controller that is actually working on the optimized trajectory and providing the action controls to the steering, the powertrain, and the brakes systems. So let's talk again a little bit about the passenger expectations. So when we think about passenger expectations, we identified 2 different topics that work in conflict when deciding what trajectory we should follow. The first topic is the motion efficiency, and the other one is motion ride comfort. So motion efficiency is related to the total distance traveled and the time spent to move from the point A to point B. So here we include, for example, the lateral speed of the vehicle, the lateral error, the heading error of the vehicle. And typically in motion comfort, we consider variables as the longitudinal and lateral accelerations, the derivatives of it, so the jerk, and also many other performance indexes or metrics that we could basically apply or calculate from specific maneuvers that would help us to correlate or to explain the level of comfort that the passenger is perceiving. Okay, so how we combine all these 2 things is basically by considering all these variables and weights in our cost function, and then putting them in the optimization process of the Mpc Motion Controller to optimize the trajectory and then give the correct control outputs and the correct motion and vehicle states. But here we want to raise another question, and is that is the part that relates to motion comfort of the coin function really capable of predicting the level of comfort of that the passenger is perceiving? This is our main question here in this project, and the way we see it is we are doing actually one assumption, which is the parameters and the variables that we are using in our cons function, but we can also use the driving simulator and these experiments that we will explain later on to actually validate the proposal that we are doing in our cons function, and also to enrich with further analysis the capability of predicting the level of comfort of the passengers. Okay, so it takes me to the next part, which is explaining a little bit about how we are setting our scenarios. The scenarios are defined based on some use cases that were agreed within the SUAVE project. But we, from our ride and comfort vehicle dynamics point of view, we are mostly focusing on three main areas of testing, which are the rural area, highway area, and urban area. These are predefined based on the Scanner European maps, and each of the areas should be tested independently. For each of these tests of independent areas, we assume a duration of less than around 6 minutes duration, and that's including even some time for the passengers or the participants to provide feedback or to reply questions about their comfort feel. From these scenarios, we are using two different groups of data. The first group is offline data, which is the minimum data that our MPC requires to define optimized trajectory. This is basically GPS coordinates of the road center line in a route that we have previously defined, the position of some static signals and speed bumps that we use as references as well, and also the locations where we want to stop and give the time for the participants to reply our answers. Then the online data is we use it to generate additional test conditions related to moving objects. So we also consider the possibility to create this interaction between the moving objects that appear in our scenario and how the Mpc controller and how our logic is going to interact with them to modify the trajectory and do something else apart from what it would typically do in a road without any traffic or any moving objects. So typically for the online data, we'll be managing scenarios like having a pedestrian crossing the road or having a vehicle in front of us that we want to follow behind in a traffic jam or in a highway. Okay, so that was an overview of the scenarios. Let's talk a little bit about our Mpc Motion Controller. We introduced the concept of the cons function, but then the reality is that in our cons function, we have more than 25 parameters that we can change or modify, and that give us plenty of possibilities to tune and set our Mpc Motion Controller. Our objective here in this part is basically to define at least 3 tuning settings of our Mpc Motion Controller, that they provide 3 different levels of comfort, and they can be easily assessed or distinguished by our expert drivers. So we are targeting to have 3 sets of our functioning modes of our MPC, which are the urgent, the base, and the comfort. We start them from more than 25 parameters. We do a pre-selection of them by doing some simulation work we are already doing. And then we also count with the help of our subjective experts and the use of the DIM 250 to actually tune and refine the configurations of our MPC controller to make sure that those functioning modes are aligned with expectations of subjective evaluation. Here, what we show is the typical scale that our experts are using during the subjective evaluation, and therefore we are kind of intending to have these different modes matching with a rating or a score of 4, 6, and 8, which corresponds to the poor performance from the point of view of comfort and neutral performance of a very good performance. Here on the right, I can also introduce a little bit the different scale that we will use in the experiments. This is the scale that our participants, naive participants, will use during the simulations. Okay, so in order to make everything work, we also face several challenges to integrate our Mpc controller, and we wanted to highlight here a few. The first one is the low speed simulation. For those that are familiar with vehicle dynamic simulation, know that tire models typically don't work very well for low speed. So we had to add some additional controllers in addition to the Mpc that can actually manage these specific conditions. We're also adding some additional logic to work on the blending or integration of these different controllers and how we get from reuse to another, from one to another during the experiment. We mentioned before the dynamic event, the dynamic events interacting with moving objects. So we are adding also that layer of logic to read and use that online data to modify the settings that our trajectory optimizer is using. And this is key basically to being able to simulate those specific events that we were mentioning before. And obviously we face also the problem of compiling and making our Mpc controller running in real time, which is something that has been solved by compiling and max function in MATLAB. Here you can see some examples of two functioning modes of our Mpc controller. On the left-hand side, you can see the urgent mode, and on the right-hand side, you can see the comfort mode. So these videos are all synchronized in time, but you can see that the level of accelerations here in this diagram is completely different between the two different modes. So on the left-hand side, the urgent mode, we are reaching levels that they go even above 0.6 meters per second square. And then on this right-hand side, we are basically limiting the motion of the vehicle to much lower levels of lateral acceleration. This obviously is in line with the values of speed that the vehicle is providing, or the Mpc is providing, because it's basically limited by also the accelerations, and because of the different configuration of the weights of the different variables that we use in the cost function. This is just an example. We said we will have 3 different modes, and yeah, more refining to work on this before we do the experiments itself. Okay, let's talk about the next part, which is the passenger data collection. We mentioned before that we are focusing on 3 testing areas. We have 3 different Mpc modes, and we are also aiming to have 10 participants testing each of the areas that we have. So that makes a total of more than 90 tests to be performed within this project. We're going to recruit between 10 and 39 participants, that obviously they need to be familiar with the driving simulator. We're going to run off-simulator and on-simulator questionnaires. This means that we ask them questions directly during the simulation by using the touch screen that we have in the Mpc, but we also have additional questionnaires that we will use offside the driving simulator. In parallel, we are also acquiring some objective physiological data to be analyzed and correlated later on with all the rest of the data we are collecting. We have concerns in the beginning about how to control the bias of the reference point, because these participants are new, and if they come to the simulator and they start testing one specific mode, that will use as reference for the following one. So we are basically changing the order of the way that we test or simulate the Mpc modes with our participants. And we are asking them not to do anything during the vehicle. Basically, they are free to focus on the road and the scenario, and we can only ask them to basically look at the screen when they have to reply the questions that we have ready to assess the level of comfort. And let me show you also a summary about all the different data that we are collecting. And you can see here that in addition to the subjective and the objective data, the comfort and the physiological data, we are also taking care of the motion sickness. So for the motion sickness, we run a susceptibility test for all of our candidates for the experiments, just to minimize the risk of them getting sick in the driving simulator. So we do a pre-selection of candidates that we ensure at least that they don't have a high tendency of getting motion sick in a driving simulator. Then we also record some occupant behavior, and that was to be analyzed by experts in the next phases of the project. We have our pre-test questionnaires, which basically we use to set our baseline references for the physiological measurements and also for the comfortable status or healthy check of the participants. We have specific questions that we raise during the simulation, asking basically for the score to the section that they have experienced. We have the continuous measurements of the objective data, and finally the post-exposure questionnaires that will help us to on one side collect like more an overall feeling about what they thought about the experiments and in the specific area or Mpc mode that they were testing, and also the chance for the participants to give additional comments that they can also be analyzed later on. Motion sickness, you can see that is anyway being monitored at many points during the experiments, just to keep an eye about the possible difference of the ratings and the data that we are collecting. Okay, so the next part, which is the data analysis. Okay, we mentioned that we are acquiring vehicle state variables from the simulator, also physiological data in a continuous way, and we also know the Mpc construction settings. One of the problems that we have here is that the subjective feedback and the information that we collect from the subjective point of view is not following the same sample rate as we have for the continuous variables. Obviously, this belongs to specific questions that we ask, and we could have around from 5 to 10 different questions for each of the test areas that we are testing. So we need to post-process the continuous measurements, the physiological and vehicle state variables, to make sure that we at least classify the data within the same section that the subjective data was collected, so we can use it for a correlation analysis later on. And in addition to the section, we are also looking at classifying different maneuvers. So basically, we look at, for example, if between this certain period of time there was a braking maneuver, we want to actually capture that classified, so we are able to apply a specific post-processing to calculate metrics that they could be then useful for the analysis later on. In the end, we are combining all these different data sets and merging them to be able to run a correlation analysis. And the purpose of this correlation analysis is basically to identify and assess the level of correlation that we have between our cost function settings and the subjective feedback that the participants were given. And an ultimate goal is basically to be able to enrich and improve the comfort index modeling, so we can have a better prediction for later phases of the project. Okay, so that was the details of the ride and comfort experiments. I would like then to highlight a little bit of the conclusions and the next steps that we are facing in this SUAVE European project. So first of all, I think that the combination of the Mpc logic together with the driving simulator, it is what it is allowing us to actually assess the ride and comfort in an autonomous vehicle in a very highly controlled environment. So we think that without having these two tools, basically it would be very difficult to replicate the same type of experiments in open roads and not having the same type of repeatability that we are having in these settings and in these experiments that we have presented. So then second, what you have seen, the methodologies that we have explained is basically the results of the combined work of the vehicle dynamics and the human factors teams. And we honestly think that this is going to be more and more frequent from now on in the future. So this is also part of the learning curve that we are doing, at least in IDIADA. And then even though with the tools and the expertise, still the data analysis approach is something that is very, very important. And we see here is it is very important to have basically a background of data analysis from the vehicle dynamics point of view. So the capability to define new key performance metrics and to assess the correlation with subjective data. And we think this is crucial for the basically for the future of the project, and to be able to obtain valuable insights and conclusions that we can use for the design of Alfred later on. The last 2 points are just to give you an overview about the next phases of this project. Obviously, we were expecting to have some results for this conference, but due to the current situation, we had to postpone many things. And now we are in the phase of refining the tuning of our Mpc modes. So as soon as we get to the office, we will have our subjective experts helping us to refine these modes. And we expect to be able to run the first experiments in June of in next month of this year. Then the activities that are planned is basically to analyze the data, to improve these comfort indexes and cost function, and to integrate everything together with the rest of the work that other partners are doing, and to put it together in the design of Alfred. That again needs to be validated next year. So we expect also by the middle of next year to be able to do a second loop of validations with a more complex approach. In parallel, we are anyway maturing the simulation scenarios and adding more complexity. So the validation that we did at the end is actually a bit more complex and can give us a bit more confidence of the results that we are obtaining. And yeah, that was the end of my part. Thank you very much for the presentation.